Hello everybody, my name is Brandon Burns. I'm the owner of National Triad Defense in Las Vegas, Nevada. I'm a firearms instructor, a former United States Army Iraq veteran, and today I'm going to be making a video to present to you and bring awareness to the world of a new scientifically advanced nanotechnology coating, unlike anything the world has ever seen before. Now, what if I told you that this coating was so scientifically advanced that it actually bonds on the atomic level? Meaning that once actually applied to any surface, it actually creates a molecular bond. It becomes the surface itself. In the coating industry, this is called an ionic covalent bond. Covalent bonds are the strongest of all bonds. This stuff is so strong, so advanced, that most acids on Earth cannot even rip it away. Over the last several weeks, we've conducted a series of very intense tests on multiple types of metal to include aluminum and steel, which are the basic metals that most people will find out there. The type of tests that we've actually done include fine caliper measurers to include measuring thicknesses. Not to mention, we will be doing a series of high-intensity heat torture tests to go along with muriatic acids, aircraft-grade paint strippers, salts, and many different other types of abrasives such as acetones and regular scratch tests. In this video, you will be able to see the actual footage of these tests being conducted on these pieces of metal. You will notice the difference between that and a normal based aerosol can paint. You're in for a ride. Now in this video, I'm going to be showing you some very intense chemicals, very strong concentrated acids, and paint thinners to include very abrasive chemicals as well. It's very dangerous what I'm about to be doing. So before I get into showing you the videos, I must change. Well, now that I've got this covered, we can go ahead and begin our test. One thing that is very important when it comes to testing surface coatings is how thick is the coating itself when added to any surface. What we did was we took a very fine caliper measure and measured every metal piece to include our aluminums and steels, and we took two measurements from millimeters to include inches. Now what we have noticed on every single coating, whether it is one layer or three layers, you only get thousandths of an inch thickness on any surface. The reason that is because once actually sprayed, it actually goes deep into the pores and sucks inside, not sitting on top of the surface like most epoxy coatings, which tends to make them thicker. Now what we've noticed is even after adding color additives such as reds, greens, blues, blacks, the thickness is still extremely small. So when you're dealing with a surface where tolerances are very fine, this coating is extremely forgiving. And not only can you add colors, which are endless amounts of options that you can come up with, you can do it in a clear finish, in either a matte finish, which keeps the shine dramatically drop down, or you can do it in a gloss finish, again adding more higher shine. Options truly are endless. Alright, let's get down to business. What is this stuff and what can it do is what you're asking me. In this can, I'm holding the world's most scientifically advanced nanotechnology coating. What is nanotechnology? Well, first, nano means billionth of a meter. The active ingredients inside this is quartz. Quartz is one of the hardest materials on the planet. Right around 75% on the Rockwell diamond hardness scale, diamond being 100, meaning it is 75% the hardness of diamonds. Now this stuff is at 5 nanometers, 5 billionths of a meter. That means the stuff is so small that it allows it to go in those microscopic pores and then it actually bonds on the molecular level. That's where the atomic level comes into play. Now at about 300 to 800 a gallon, it is pretty much considered liquid gold to me at this point. Now before we start all the torture tests, I'm going to show you a quick color, shine if you will, of all the pieces that we've coated. And just because I know you guys want to really get into it, we're going to start off by using torture fire tests. And just to prove the temperatures that we're getting up to, I got a laser thermal gauge reader to show you the temperatures we're dealing with. So let's get into this and we'll have some fun. First test I'm going to show you is a bending test. This side has been coated, this side has been uncoated. Most paints and most adhesive paints, if you bend the surface, it will start to crack at the seam. So we're going to go ahead and bend and show you if there's any cracking. We'll start with a corner. And you can notice there's no cracking. So let's go ahead and bend it even more. Again, no cracking, no flaking, no peeling, even on the reverse side. Bend it again backwards to a full bend. Still no cracking, no flaking, or no peeling. Let's go ahead and try to straighten it out best we can. And just give it a few more bends. So we definitely took the pliers into it quite a bit. You notice not a lot of actual real scratching and no cracking or flaking on the coating. So the integrity of it is very strong to abrasion and bending, especially on aluminum. Alright, time to get down to the fun stuff. So now I have a piece of that same aluminum that I just got done bending and tortured the heck out of it. This side is coated, this side is uncoated. Right now, we're going to torture test it with heat, use a thermal reader to collect temperature, and then dunk it in water right after to shock it, which will give it an extreme test on the coating's integrity. So, without further ado, temperature of the metal is reading 80 degrees Fahrenheit. Let's burn. So what I'm doing here is I'm going to gradually heat the metal instead of just directly blowing the torch right on this one spot. That's more realistic to simulate heat by gradually heating up the whole thing. Of course, if you sit there and hold a torch directly to metal, it is going to melt it. That's what they do. Now right now, you're noticing no bubbling, no flaking, or no peeling off of the coating itself. Most paints or coatings by this stage will already bubble or burn away. Yet this is holding strong, holding a good shine, and not really noticing anything. So let's go ahead and temperature test it. We are at 350, 380 degrees. 380 degrees Fahrenheit. Let's go a little bit more. At this stage, the metal itself is turning yellow. It's actually tarnishing because of the heat. So the metal underneath is actually discoloring because of the heat before the coating itself has been affected. This right here is the power of nanotechnology, people. So let's give it one more heat test. We're at 460 degrees Fahrenheit. Go ahead and turn off the torch. And what we'll do is shock the metal itself. By actually dunking it in water, it should make the coating flake or bubble away. You can hear the sizzling. And notice it it is still extremely super hydrophobic, which means the water just rushes right off of it. The coating itself is perfect. It is shiny, it is flake free, it is bubble free, and it is literally still into the atoms very deeply. Okay, here we have a piece of blue nano coated steel. It's a very dark blue. And then here we have a piece of black matte nano coated steel. That's hard to see, but this is gloss, this is matte. The shine is dramatically reduced. We're going to show you a heat torture test on this and see how hot it can get and see if the color or coating even flakes or bubbles away. Okay. What we're doing is gradually heating both pieces simultaneously and not holding the torch directly on it, which is not realistic. We just want to gradually heat the metal from room temperature to as hot as we can get it. Here in about 20 seconds, I'm going to take my laser thermal reader and read the temperature of what each piece of this metal is. Each of these are about 150 degrees. We are now at 274 degrees each. Still no bubbling or flaking. No discoloration in the metal or color. We're at 482 degrees at peak. Still very, very hot. So let's just go ahead and take it overboard. Let's go ahead and heat up the blue as much as we can. 400, 360, 480, right around 400 degrees. Still nothing. Over 400. Very, very high temperatures, yet we're still not getting any cracking. So I'm going to go ahead and turn off the torches now. You get an understanding of how much heat this stuff can take. So even after an extensive heating test and dunking water on it immediately after, the coating integrity is still completely intact. Still strong, still very, very high scratch resistance, still very, very smooth coating, and waters and acids and oils still drip right off of it. Now, to demonstrate its heavy chemical resistance, we are going to take muriatic acid and then soak each metal piece in that acid, which will actually start to dissolve it. Right here, we have a piece of regular aluminum steel, uncoated, which you can see. This is basically how it would come from any factory or how it would be put up at any construction site. Go ahead and drop that in the acid. Actually, if you notice, the reaction is instantaneous on this one. It's actually already starting to bubble and heat up. Here we have a piece of aluminum coated with our nano gloss coating. Go ahead and drop that in. Instantly you notice a huge difference, no bubbling between the difference. Here we have a piece of blue, I know it's hard to see, but blue nano coated. And then we have a piece of black matte nano coated metal as well. Now we'll all let those soak. Notice the bubbling of the regular aluminum and no chemical reactions with the others. Okay, ladies and gentlemen, as you can now see, we are over 5 minutes in, and the regular uncoated steel is already completely bubbling and melting away with a chemical reaction. Yet our nano-coated pieces still show no signs of chemical wear or resistance. The coated metal, the blue-coated nanometal, and the black matte-coated nanometal still show no signs of chemical corrosion. Just to show you how dangerous this is, we are dealing with over 100 degrees Fahrenheit just from dropping metal in a liquid. And that is the chemical reaction. That's the power of nanotechnology. Okay, now to simulate scratch resistance and an extra chemical corrosion resistance, I'm going to take a couple of pieces of metal here, put aircraft grade paint remover on it, and then take a steel brush and try to scrape the paint off by force. Let's begin. First one, normal aerosol can paint, Krylon. Not using that much force, I'm going kind of light on it. And already we notice it came off very easily. We're already at the steel now. Now we're going to move into the matte black nano bionic coat. Okay, I went a little extra harder on this one because it's the coating, so I wanted to punish it more, and not much of anything really happened to it. Nothing like what you saw with the Krylon. Whew, this stuff's harsh. Now the blue coating, gloss. Still, almost no paint came off, no coating came off. Very high scratch resistance. That's because of the quartz active ingredient, which again is almost 75% hard as diamonds, so that's why it has such high scratch resistance. Last but not least, we'll take bare steel coated with the gloss nano coating. No paint, no additive, no color. Here. And I'm noticing nothing. Very, very few scratch marks even from the brush. That's because of the very high scratch resistance of the coating. The coating is still there. If I dip it in water, it's still very hydrophobic. The water doesn't really even want to stick to it. Now, because of this coating's unique properties, it also makes maintenance and cleaning dramatically reduced on any surface that you put it on, because there's no longer any pores for any dirt or molecules of oil to get into. Everything sits on the surface. That way, easy to be cleaned, easy to be wiped off. That's why it has such high corrosion resistance as well, because nothing can get into the lower atoms of the substrate. So here I'm going to show you a few things. Here I have raw aluminum with a Sharpie marker over it, which simulates graffiti or anything going into the pores. just a normal household cleaner right here. We'll go deep on it. I'm going to scrub pretty deep. And just to be extra harsh to try to clean it really good, I'm using acetone. And I scraped it pretty good, but if you can see, there's still an outline of a face in there. That's heavy graffiti deep into the pores. I would have to seriously scrub hard with this and get a wire brush to get it out. I've been scrubbing here with acetone, which should have removed it immediately, but still, it's still in the surface. So let's move on past that. So let's take a piece of coated aluminum, Bionic coated aluminum, and see how easy this is to wash off. One swipe, it's completely gone. Very fast. I barely even did anything, completely gone. This was sandblasted aluminum. Let's do polished aluminum. Immediately gone. Very easy to wipe off. If this was carbon, graffiti, anything, normal chemicals will wash this off easy. You can use common household chemicals like your normal cleaning products. Let's move on to raw steel. Now raw steel, again, this is you know, your beams, your houses, or buildings, firearms, guns, this kind of thing. Acetone, again, I have to scrub pretty deep. Scrubbing very, very deep. And the face is still in there. If you can see that, the smiley face is still in there. I would have to scrub very, very hard. Get a wire brush, the face is still in there. Again, another coated piece of aluminum, steel, face wipes off immediately. Another piece of polished Bionic coated, wipes off immediately. How about a little bit of green color Bionic coating? Wipes off immediately. If somebody spray paints your car, spray paints your walls, Sharpies something, easily to clean, easy to remove if it's graffiti. If you have carbon deposits on something, dirt deposits on something, oils, it all wipes off the surface. That's what makes this so strong, is because it fills in those pores and doesn't allow things to get in the surface. That's the power of nanotechnology.